Hello, everyone. Let's talk about the ideal gas law, otherwise known or affectionately known as PIV-NERT. And PIV-NERT is, again, no, I'm sorry, to start off with, is an equation of state. In other words, how is the gas right now? So P is pressure, V is volume, T is temperature. Okay. Some things you might not know, although we did just talk about it in a previous video. N is the moles of gas. Okay, that's universally what we'll talk about. Lowercase n is moles of gas. And then R is the ideal gas law, or excuse me, the ideal gas constant, and you should know that it's 0.0821 liters atmospheres over k mole, okay? And yeah, that's another thing you have to memorize, although it might be on your reference sheet for the test. So 0.0821 liters atmospheres over k mole is something that you should get in your brain. It just makes it easier. You don't have to look it up every time. Okay, so now we're going to look at how gases are at a certain point. So the gas laws are how gases are changing when you change the conditions. This is how gases are right now, okay? So if we do a couple problems, it's actually not too bad. So you have calcium carbonate decomposes to CaO and CO2. A sample of CO2 is collected in a 250 milliliter flask, and the gas had a pressure of 1.3 atmospheres at a temperature of 31 degrees Celsius. What mass of carbon dioxide was generated? Okay, so this is a little strange here. So calcium carbonate decomposes to CaO and CO2. So that first sentence right away, I don't know if I have to do this, but I feel like I need to write a chemical reaction, okay? So calcium carbonate decomposes to calcium oxide and CO2, and I believe it's balanced, okay? A sample of CO2 is collected in a 250 milliliter flask, so there's a volume there. Now don't forget, if a sample of gas is collected in a flask, it's going to occupy the whole flask, so 250 milliliters we can use not only as the volume of the flask, but also the volume of the gas. The gas has a pressure of 1.3 atmospheres and a temperature of 31 degrees Celsius. What mass of CO2 is created? So it says mass. Well, if I use PIV-NERT, because I have a pressure, I have a volume, and I have a temperature, so that's PIV-NERT. Nothing's changing, so I'm not going to use PV over T. So PV equals nRT, and I need to find mass. Well, of P, V, and N, and R, and T, the only way I can get mass is with moles. So that's my X. So N is equal to PV over RT. Okay? So I think we can plug and chug here, mostly. Okay? So pressure is 1.3 atmospheres. By the way, let me just mention this real quick. Since since this is the units for our R constant, the ideal gas constant, make everything liters, make everything atmospheres, make everything Kelvin, make everything moles. Okay? Just convert everything to fit that, and life is a little bit easier in my opinion. So pressure, since that's in atmospheres, that's good. We want 1.3 atm. And the volume, 250 milliliters, that's not in liters. Again, it's liters atmospheres over k mole, the units for R. So let's get that into liters. Very simple. R, there it is, 0.0821 liters atmospheres over Kelvin times moles. And times the temperature. That's 31, of course, that's not in Kelvin. So again, we got to convert that to Kelvin. So that's 273 plus 31 gives us 304. Okay, can we cancel? Yeah, there's a bunch of stuff. Left with moles, that's good. Denominator of a denominator, that's also good. That really means it's in the it's a numerator. So now use your parentheses if you can do this. If not, then just make sure you get it correctly. So I'm going to divide by 0.0821. I already multiplied the top, times 304 and the parentheses, and I end up with 0.0130. Okay, 0.0130 is the amount of moles. So N of CO2 is 0.0, what did I say? 130 moles, okay, of CO2. Now I want mass of that. Not a problem. Let's just use our molar mass of CO2. And the molar mass of CO2 is 44.0 grams. I just added that up in my head. And we end up with, so let's multiply by 44, and we end up with 0.573. So 0.573 grams of CO2 was produced in this reaction from our mass of CaCO3. Okay? Let's try another. particular tennis ball has a volume, so there's my V, and contains 0.33 grams of nitrogen gas, so there's a mass. I can convert that to moles, I guess. What is the pressure? Okay, so again, using the ideal gas law, PV equals nRT, or PIV-NERT. Looks like P is my X here. So let's divide everything, let's divide out V over. So P is equal to nRT over V. You'll notice again, I like to get my X alone. So right away I'm starting to plug in here and I don't see any moles, but I do see 0.33 moles of nitrogen. So let's work that off to the side here. So 0.33 grams of N2, be careful, that's Professor H. Broncliffe with our 7 diatomic molecules. So that has a molar mass of 14, but 14 times 2 is 28 grams of N2, and we're converting that to moles of N2, okay? So 0.33 divided by 28 is an answer of 0.0118, rounding up. So that's my N, all right? So we just got that. So let me change colors here. 0.0118, just checking, moles. I'm going to erase this because it's going to get in my way. R is 0.0821 liters atmospheres over kmol. Whoopsie, kmol. And then T is 24 degrees Celsius. Well, that's 297, I believe. Let's just add that up times 24, or plus 24 is 297. So that's my Kelvin temperature over the volume, and the volume is 144 centimeters. Now, don't panic, that's 144 milliliters. Remember, centimeters cubed and milliliters are exactly the same thing. Well, since that's milliliters, and there's 144, we need to change that to liters to match this. So moles cancel and Kelvin cancels, leaving us with the pressure in atmospheres, and life is good because that's what they're asking us for, a pressure. So 0.0118 times 0.0821 times 297, press equals, divided by 1.144, we end up with a pressure of about 2. 1.99 or about 2.00. I think we're okay with either answer. ATM, done. Okay, so that's PIV-NERT. Okay, now the molar volume of the gases, we can play into this now. So 1 mole of any gas, but you got to be at STP. It doesn't matter what gas it is. And the reason is because the gas particles are infinitely small. Compared with humongous distances between them, it doesn't matter how big the gas particles are because they're infinitely small, no matter what gas it is. So any gas at STP will occupy something about the size of a beach ball, which is 22.4 liters. Okay? So if you have a mole of hydrogen gas at STP, what volume does this occupy? Okay? If we work with the molar volume of a gas, and since the conditions are STP, this problem becomes quite simple. So if we have 2 moles of any gas, it doesn't matter what it is. It says it's dry H2, which is hydrogen. It's at STP. And I know that 1 mole of any gas at STP occupies something the size of 22.4 liters, or about the size of a beach ball. So therefore, 22.4 times 2 is 44.8 liters. And we are done. It's really that simple. Now, I mentioned there's 2 ways to solve. There is another way to solve this, and that is by using PIV-NERT. You have a pressure, you have a volume, you're looking for volume, excuse me. So P and V and N, you have 2 moles, and then R, you know that one, and T is temperature. So it's all there. So if you forget about this, all is not lost. You can use PIV-NERT, okay? But the molar volume of a gas says that any gas, if you have 1 mole of any gas, but you got to have STP, that'll occupy a volume of 22.4 liters, okay? Check this out. This is, I'm not going to derive this for you, but this is the density of a gas. It's basically, I call this dirt map, or dRT is equal to MP. This is dirt map, and this is how you solve for the molar mass, that's molar mass of a gas, okay? This pops up quite frequently. I'm actually surprised how frequent it pops up, but dirt map, dRT is equal to MP, and that's solving for the molar mass of a gas when they give you the density of the gas, okay? Again, you can work through this if you want. I am not going to do that. I just changed my mind. And then I'm going to do one gas stoichiometry problem. And gas stoichiometry, guys, it doesn't matter where it comes from. So again, with this, we need a balanced equation. So it says carbon monoxide. Let me switch colors here. carbon monoxide reacts with oxygen, don't forget that's O2, to produce CO2, okay? And it's balanced. Oh, it's not balanced. I need a 2 here and a 2 here. I think that does it. Yes. Okay, if 1 liter of carbon monoxide reacts with oxygen at STP, how many liters of oxygen are required to react? Okay, so if I have 1 liter of CO2 that's reacting with oxygen at STP, so now 1 liter of carbon monoxide reacts with oxygen, and this whole thing is at STP. It says how many liters of oxygen are required to react. So if I have that, I have liters of CO, and I could use a mole ratio here. The problem is I don't have enough information to convert to moles. I do. Now that I think about it, I can convert to moles using the ideal gas, the molar volume of the gas, the 22.4. But there's a quicker way. According to Avogadro's law, which we looked at earlier in this chapter, it says that if you have 2 gases at the same temperature and pressure, then the number of particles that they have, the moles, are directly proportional. In other words, what all that means is that instead of setting up a mole ratio, because Avogadro's law applies, you can set up what's called a liter ratio. So this is really sneaky. It's really tricky that they did this. But it makes perfect sense once you apply Avogadro's law and these kinds of problems. So instead of having a mole ratio, you're going to have a volume ratio. So you have 2 liters of CO, and then it says how many liters of oxygen are required to react. That's 1 liter of O2, and basically what that says is that you're going to have half of a liter of O2. Now this makes perfect sense. Because you have double the CO that reacts with half the amount of O2, you need half the volume of O2. So not only do our mole ratios make sense, but as long as everything's at the same temperature and pressure, Avogadro's law applies. So use a volume ratio rather than a mole ratio. Pretty cool. Okay, more gas stoichiometry. Again, this is, stoichiometry. The only thing I would be careful of is in case they slip one into you, slip one here into the problem set, and I'm just looking here as I go through these. I believe this one is a limiting reactant problem. So just be careful. Let's see here, I'm just reading it real quick. Yes, I believe this is a limiting reactant problem. Yes, it is. So just be careful. You pause the video here. I don't have an answer for you because I'm trying to keep the videos a little bit more concise, and this one's getting a little bit long, and I am done as of right now. So again, work through this, and if you have a question on what the answer to this is, I can work this in class, okay? But that's all I got for now.